Good morning, good afternoon, and good evening to everyone who joins us from around the world. We're so glad you're here. This is Andrew and Renee. Welcome to the Stack series.
It is wonderful to be back with you.
Today we are exploring mathematical modeling of infectious diseases. And I have to say, when I look at the research we've pulled for this, it feels incredibly relevant, almost heavy.
It is.
We're constantly surrounded by these phrases now, aren't we? The model says, or we have to flatten the curve. It's almost become, background noise.
A part of the daily vocabulary for millions of people who never thought they'd have to care about epidemiology.
Exactly. But I think for most of us, if we're being honest, it's a total black box. We hear the prediction, but we have absolutely no idea what's going on under the hood. What is the actual machinery that drives these things?
And that machinery is just... It's a fascinating, and you said it, sometimes a terrifying mix of biology, of sociology, and some really, really hard mathematics.
It's not just a spreadsheet. Oh, not at all. And I think that's the most critical thing to get across today. These aren't just abstract equations that academics play with on a whiteboard.
No.
These models, their outputs, they directly influence government policy. They are the reason economies shut down. They're why schools close. They inform, and this is not an exaggeration, life or death decisions on a global scale.
The stakes are about as high as they can get. It's high-stakes math.
The highest.
Yeah.
And that's why our sources for this exploration are so broad. We're looking at everything from the classical, almost 100-year-old foundations of epidemiology,
Right,
all the way up to cutting-edge network theory, agent-based modeling, and even the ethical frameworks that are supposed to keep these powerful tools in check.
So our mission today really is to pry open that black box. We want to move from that simple textbook idea of disease spread, the little red dots moving on a map like in a movie.
Right, the disaster movie graphic.
Yes. We want to get past that and into the messy, complicated, and frankly much more interesting reality of how human beings actually interact with each other and how we try, and sometimes fail, to predict the unpredictable.
Let's get into that machinery.
Let's do it. So I think we have to start at the beginning. At the foundation, what we think we know.
The bedrock.
And in epidemiology, that is the SR model. I was reading this source from Theo Vine, A Beginner's Guide, and it just hammers home that this thing is nearly a century old.
It is. It dates back to Kermack and McKendrick in 1927.
So why is it still here? In a world of supercomputers and AI, why are we still using what you called the Model T of epidemiology?
Because of its elegance. And I don't mean elegant in a trivial way. I mean, it manages to capture the fundamental dynamics of a massive chaotic event using just 3 letters, S, I, and R.
Right.
It's what we call a compartmental model. It takes the entire messy, diverse population of a country, or even the world, and simplifies it by sorting everyone into one of 3 distinct buckets. It's a way of imposing order on the chaos.
Okay, so let's walk through the buckets, because when I was reading this, I was literally picturing 3 big water tanks connected by pipes. Is that a decent analogy?
That is the perfect analogy. Let's run with it. Imagine the first tank. It's labeled S. This stands for susceptible.
So healthy people.
Healthy, but crucially vulnerable people. These are all the individuals who can catch the disease.
The fuel for the fire.
Precisely. In the case of a brand new virus, something humanity has never encountered before, that S tank is completely full. It's basically the entire global population minus a few very lucky, very isolated people.
So the tank is full, and there's a pipe leading out of it.
Yes. That pipe leads to the second tank, labeled I, for infectious. These are the people who are currently sick and, this is the key part, can transmit the disease to others. They are the spark that lights the fuel.
Okay, and this is where the math comes in, right? The flow from S to I isn't just a random leak.
Exactly. The rate of that flow, how quickly the S tank drains into the I tank, is governed by a set of differential equations.
And I know differential equations is the point in the conversation where you can hear people's eyes glaze over.
Well, let's make it simple. It just means we're calculating a rate of change. How fast is something happening right now? The main thing that controls the valve on that pipe is a parameter, a variable, usually called beta.
Beta. So what is beta? Is it just how contagious the virus is?
It's a combination of things, which is what makes it so tricky. It bundles together the biology of the virus, how easily does it jump from one person's cells to another's, with the sociology of the population.
How people behave.
Yes. How often do people have contact? How close do they stand when they talk? Do they shake hands? Do they wear masks? All of that human behavior gets mashed together with the virus's biology into this one number, beta.
So a high beta means the valve is wide open.
Wide open. The S tank drains into the I tank almost instantly. On a graph, that's your terrifying vertical spike. A low beta, maybe because people are social distancing, means the flow is just a trickle. The valve is almost closed.
Okay, that makes sense. S to I. That's the third tank.
The R tank is for removed. Now, sometimes people will tell you it stands for recovered, and in a good outcome, that's what it is.
Yeah.
But the technically correct and more comprehensive term is removed.
Removed sounds a bit final.
It is final from the perspective of the epidemic's dynamics. It means a person is no longer part of the transmission chain.
For one of two reasons.
Right. Either they have successfully recovered and, crucially, now have immunity, so the virus just bounces off them, or, tragically, they have passed away. In either scenario, they can no longer get the disease and they can no longer spread it.
So the fire has used up that piece of wood. It can't be burned again.
Perfectly put. So you have this one-way flow. People start in S, they flow into I at a rate governed by beta and the number of infectious people, and then they flow out of I and into R at a rate we call gamma.
Okay, so gamma is the recovery or removal rate. How fast people get out of the infectious stage.
Yes. If you have a disease with a short infectious period like a common cold, gamma is high. People move into the R tank quickly. If you have a disease where people are infectious for weeks, gamma is low, and that I tank stays dangerously full for a long time, infecting more and more people from the S tank.
This whole flow, S to I to R, it's so simple, but it leads directly to the most famous number in this whole field, the one we all heard about constantly. R naught. R is 0.
The basic reproduction number, yes. It's probably the single most influential variable in all of public health policy.
So what is it exactly? It's not just a number, it's a concept.
It's a concept derived directly from those flow rates we just talked about, from beta and gamma. It represents the average number of new infections that a single infected person will cause in a population that is 100% susceptible.
So at the very beginning of an outbreak, when that S tank is totally full.
That's the basic part. Is the virus's raw, unchecked potential in a completely naive population. If R naught is 3, it means the very first sick person will, on average, infect 3 other people.
And then those 3 each infect another 3, so that's 9.
And those 9 infect 27.
81. And suddenly you have exponential growth.
That's the terrifying power of greater than 1. And this brings up the idea of the epidemic threshold. It is a mathematical tipping point, a line in the sand.
The magic number is 1.
The magic number is 1. If R is below 1, even if it's 0.99, each generation of infections is smaller than the last. The epidemic is guaranteed to peter out and die. The fire runs out of new fuel faster than it can spread.
But if R is above 1, even just 1.1, each generation is larger than the last. It will grow.
It will grow. And the goal of every single public health intervention, masks, lockdowns, vaccines, is to take that R naught, that raw potential, and wrestle the effective R, the R value, right now, down below 1.
It sounds so clean when you put it like that. So elegant.
It is.
But, and this is a huge but, this whole beautiful, simple SR model is built on a foundational assumption that when you say it out loud, just sounds wrong.
You're talking about the homogeneous mixing assumption.
I am. It sounds like something you'd do in a chemistry lab. Mix the solution until homogeneous.
And that's exactly the right way to think about it. The model, in its purest, simplest form, makes a radical simplification. It assumes that every single person in the population is equally likely to come into contact with every other person.
It treats all of human society like gas molecules bouncing around randomly inside a sealed jar.
A perfectly stirred solution, yes. It assumes that your chance of getting infected by your next-door neighbor is exactly the same as your chance of getting infected by a random person in a city 1,000 miles away.
Which is, I mean, it's just self-evidently not true. My world is small. I interact with my family, my coworkers, the person at the grocery store. I don't have random contact with the entire population of the United States.
Of course not. And that is the single biggest, most obvious flaw in the classical model. It completely ignores the structure of human society.
The network.
The networks. The fact that we live in clusters. Families, workplaces, schools, communities. The model ignores that a kindergarten teacher has a fundamentally different contact pattern than a lighthouse keeper. It treats us all as generic, interchangeable units of humanity.
And I think that's where you start to see the evolution in the math.
Yeah.
We have this paper from Abdul Rahman and others on modeling COVID-19, and you look at the equations in this paper, and it is not S, I, and R anymore.
Oh, it's an alphabet soup.
It's an explosion of complexity.
It is, because that's the first step modelers take to make things more realistic. They start adding more compartments, more buckets. The first and most common addition is moving from SEIR to SEIR.
The E.
The E stands for exposed. This is a crucial addition. It creates a bucket for people who have been infected. They have the virus in them, but they're not yet infectious to others. The latency period.
So it adds a delay to the system.
A critical delay, because it helps explain how silent spread can happen. People can be walking around feeling fine in this E compartment, and then a few days later they move to I and start the transmission chain. Without the E, it's harder to model that lag.
And then in the Abdurrahman paper, they don't stop there. They add V for vaccination.
Right, which is a pipe that goes directly from the S tank, the susceptible tank, and moves people straight over to the R tank, the removed tank, without them ever having to pass through I.
They get a get-out-of-jail-free card.
A biological bypass.
Yeah.
They also add Q for quarantine and H for hospitalization.
So they're just adding more and more buckets to try and capture the reality of what's happening.
They're trying to model our interventions. The basic SR model is like watching a natural process unfold. But we don't just watch. We fight back. We pull levers. We can take people from the I tank and put them in the Q tank, which is like putting a lid on them so they can't infect anyone else.
So the math gets much, much messier.
Incredibly messy.
But the goal is to get closer to reality.
But there's a catch here, isn't there? Even with all these extra letters, SEIR, VQH, you're still basically dealing with big anonymous groups of people.
You are. You're still, at a fundamental level, assuming homogeneous mixing within each of those buckets. You've just made the bucket smaller and more specific.
So you're still not capturing the structure.
Not really. To do that, you have to throw out the idea of buckets and tanks altogether. You have to stop thinking about fluids and start thinking about connections.
Which brings us squarely into our second section, the active debate. This is where the science gets contentious, where people really disagree, and it's this shift from mixing in a jar to network theory.
This is a complete paradigm shift. It's a different way of seeing the world. Instead of populations flowing between states, you start to see society as a gigantic, intricate web.
And in this web, each person is a node, a dot. Right. And in our relationships, our physical contacts, the people we live with, work with, talk to, those are the edges or the lines connecting the dots. And the virus. It's not a fluid anymore. It's something that can only travel along those specific lines. It can't just magically jump from one side of the web to the other.
Now, for a long time, there was this one really dominant idea about what that web looks like. It was called the scale-free network. I remember reading about this in the early 2000s, and it felt like it explained everything.
It was the darling of network science for more than a decade. The idea was that most real-world networks, from the internet to protein interactions to human society, followed this one specific architectural rule.
And that rule is that they are dominated by hubs.
Exactly.
Yeah.
The perfect analogy, which gets used all the time, is the airline route map.
Okay.
If you look at all the airports in the world, most of them are small, regional airports. They might have a handful of connections to other nearby cities. They're the vast majority of the nodes.
Right, your local airport.
But then you have a tiny number of massive hubs. London Heathrow, Atlanta's Hartsfield-Jackson, Dubai. These are nodes with an enormous number of connections, thousands of them, linking to all parts of the globe.
So the idea was that human society is built the same way. Most of us are the small regional airports with our little circle of friends and family.
But there are a few superconnectors. These social hubs, these super spreaders, who are the human equivalents of Heathrow, they have a disproportionately huge number of connections.
And if that's true, if society is really built like that, it has massive implications for how you fight a pandemic.
It gives you a clear, almost surgical strategy. Forget about trying to vaccinate everyone. Just find the hubs.
Go after the super spreader.
Exactly. If you can identify and neutralize those few critical hubs, vaccinate the superconnectors, isolate them, the theory says the whole network will fragment. It will break apart into lots of little disconnected clusters.
You take out Heathrow and Atlanta, and the global air network effectively collapses. The virus has nowhere to go.
It's an incredibly efficient, targeted strategy. It sounds perfect. It's the silver bullet.
I sense a very large but coming.
A very large but. We have a source here from Closet, Shalizi, and Newman, and the title says it all. Scale-free networks are rare.
Rare? I thought they were supposed to be everywhere.
That was the belief. For a long time, researchers were fitting this model to everything. The internet, citation networks, social webs. It became this default assumption. But what Closet and his team did was apply much more rigorous statistical tests to real-world data. They didn't just look for a pattern. They tried to prove it was there, statistically.
And what did they find when they looked at the data with these stricter tools?
They found that while many networks have hubs, very few actually fit the precise mathematical definition of a scale-free network. Most of them have a scale. There's a point where the number of connections starts to fall off much faster than the theory would predict.
Why is that? Why don't we have these human Heathrows in the way the model would suggest?
Well, think about the physical constraints. An internet server, a hub like Google, can have millions of connections. There's no real physical limit. But a human being...
There's only 24 hours in a day.
Exactly. You physically cannot maintain the kind of meaningful, disease-spreading contact with 10,000 people that a true scale-free hub would require. There are cognitive limits, time limits, physical limits. There's a natural ceiling on how many connections a person can have, which you don't see in digital networks.
So the implication here is massive. If our public health officials have been designing strategies for the last decade based on this idea of targeting these super hubs,
And the real-world network isn't actually built that way.
then the whole strategy could be fundamentally flawed. You might be pouring all your resources into vaccinating the people you think are hubs based on a flawed model.
While the virus is actually spreading quite happily through the dense middle-tier connections that your model told you to ignore, you're hunting for a monster that doesn't really exist in the form you imagine it.
It's a huge potential blind spot. It shows that getting the structure of the network right is just as important as understanding the biology of the virus itself.
It's everything. And this connects directly to another debate that's highlighted in this Bifolchi paper, which looks at spatial approximations.
This is a really interesting question. Can't we just use geography? Forget all this complex network stuff. People infect the people near them. My neighbor gets sick, then I get sick. Why not just use a map?
It's a very tempting simplification. And for some things, it works. We call it a spatial model. The classic analogy is a forest fire.
Okay.
A tree catches fire. It ignites the trees immediately next to it. Those ignite their neighbors. You get this wave of fire spreading across the landscape. It's a purely geographic phenomenon.
And the Bifolchi research found that for epidemics, this kind of spatial model works, but only under very specific conditions.
It works well only if the vast majority of contacts are short distance. If you're modeling a disease in an isolated medieval village where nobody ever leaves, a spatial model is probably great. The disease will spread house to house, like a wave.
But we don't live in medieval villages.
No. The moment you introduce long-distance connections, what network scientists call small world shortcuts, like air travel, the spatial model completely falls apart.
Because the fire doesn't just spread to the next tree. It suddenly jumps 1,000 miles and starts a new fire.
Exactly. A person gets sick in New York, gets on a plane, and starts a new independent outbreak in Los Angeles. A spatial model, a forest fire model, simply cannot account for that. It will always underestimate the speed and scale of the spread.
It's the difference between tracking a forest fire and tracking a rumor on the internet.
That's a perfect way to put it. A rumor doesn't spread to your next-door neighbor. It spreads to your followers, who could be anywhere in the world instantly. Modern pandemics are much more like internet rumors than forest fires.
So the network reality, with its long-distance jumps, just breaks the simple geographic model.
It shatters it. And the Bifolchi paper showed this in their simulations. They created these networks and found that even adding a tiny number of random long-distance links dramatically accelerated the pandemic beyond what any spatial model could predict.
And they also looked at superspreaders in those simulations. This is interesting because it links back to the scale-free debate.
It does, because even if Closet is right and networks aren't truly mathematically scale-free, that doesn't mean everyone is equal.
Right. Not scale-free isn't the same as uniform.
A crucial distinction. The network might not have the extreme hubs the theory predicts, but it absolutely still has what we call a fat tail distribution. Most people have a few contacts, some have a moderate number, and a few people have a lot. A bus driver, a teacher, a bartender.
The choir singer.
The infamous choir singer example. And what the simulations show, time and time again, is that these individuals, even if they're not a mathematically perfect hub, have a massive outsized impact. They are accelerators. They can single-handedly change the trajectory of an outbreak in their community.
So the takeaway is you can never assume that people are average.
Never. The average person is a statistical fiction in epidemiology. It's the outliers, the exceptions, the people in the tail of the distribution that drive the chaos and shape the outcome.
And speaking of chaos, let's push into the third area, the frontiers. This is the really cutting-edge stuff that might change everything we've just discussed.
This is where the math is really straining to catch up with the sheer complexity of human behavior.
And for me, one of the most mind-bending concepts came from the Steinmeier paper. It's this idea of polyadic interactions. Now, please, break this down for us. What is a polyadic interaction, and why does it matter?
Okay, so almost every model we've discussed so far, even the complex network ones, makes a fundamental assumption that infection happens in pairs, a pairwise interaction. Person A infects person B. It's a chain of one-on-one events. A disease travels along an edge connecting two nodes.
But that's not really how we live our lives. I'm rarely in a room with just one other person. We're in meetings, we're in classrooms, we're on crowded buses, we're in choirs.
Exactly. Those are polyadic or higher order interactions. The infection isn't a one-to-one transaction. It's a group dynamic. The exposure is happening simultaneously among a group of 3 or 10 or 50 people.
And you need a whole different kind of math to even describe that.
You do. You move beyond simple graphs with nodes and edges and into things called simplicial complexes. It's a way of modeling group connections, not just individual ones.
So what happens when you build a model that way? The Steinmeier paper found something really shocking. They talk about a phenomenon called B-stability.
This is a huge deal. It's a fundamental shift in how we think about outbreaks. In a classical pairwise model, as the conditions get worse, say the virus becomes more contagious, the amount of disease in the population ramps up in a fairly smooth, predictable, linear way.
A gentle slope.
Right. But in these polyadic group-based models, something strange happens. The system can get stuck.
Stuck in what way?
It can remain stuck in a completely disease-free state, even when the underlying conditions, the contagiousness of the virus, are getting really, really bad. The structure of the group interactions somehow provides a collective resilience. It holds the disease back.
That sounds good.
It is good until it's not, because it holds and it holds and it holds, and then you push the system just one tiny fraction more.
And it snaps.
It doesn't just snap, it crashes.
Oh, sure.
The system jumps almost instantaneously from having zero disease to having a massive full-blown outbreak. It's not a slope anymore, it's a cliff edge.
An explosive transition.
That's the technical term for it. And it is terrifying from a public health perspective.
Because it means all your warning systems could fail. You could be looking at your data day after day and seeing zero cases thinking, great, our control measures are working perfectly.
And you're standing right on the edge of the cliff and have no idea. One more small push, one super spreader event in the wrong group, and the entire system collapses into an epidemic overnight.
Wow, so it helps explain those outbreaks that seem to come out of absolutely nowhere.
Exactly. It suggests that our social structures can act like a dam, holding back the pressure until it reaches a critical point, and then the dam doesn't leak, it bursts. If you're using a linear model, you will never, ever see the dam break coming.
That's a really powerful and unsettling idea. And it ties into another frontier concept, this one from the Park et al. Paper, which is about how we analyze new variants.
Ah, yes, the speed versus strength debate.
Right. We hear on the news that a new variant is more contagious or more transmissible, and our brains, in many of the simpler models, immediately interpret that as meaning that it has a higher R0.
We think of it as strength. The new variant is like a stronger boxer. It punches harder and is more likely to cause an infection upon contact.
But the Park paper argues that's only half the picture. We also have to look at speed. And they introduce this crucial concept of the generation interval.
The generation interval is simply the average time it takes from when I get infected to when I infect you. It's the turnover time, the pace of the epidemic.
And the insight here is really counterintuitive, but so important.
It is. The paper demonstrates that a new variant could be spreading like wildfire, not because it's stronger. Its R0 might be exactly the same as the old variants, but simply because it's faster.
It has a shorter generation interval.
Yes. Think of it like compound interest. If I infect you in 3 days instead of 6 days, the virus is completing twice as many generations of spread in the same amount of time. Each cycle might not be bigger, but they're happening much more frequently. The compounding effect is enormous.
So if public health officials are only focused on calculating the strength, the R0, they could be completely misjudging the threat.
They could be massively underestimating it. A faster virus can lead to a much steeper, more explosive wave of cases, even if its R0 is no higher. If you confuse speed for strength, you get your predictions for when the epidemic will peak completely wrong. You might think you have weeks to prepare your hospitals when, in fact, you only have days.
A fast virus is a logistical nightmare.
Even if it's not a stronger one. That's the key.
Now, all of this modeling networks, generation intervals, polyadic interactions, it all depends on having data. But what happens at the very beginning, day one of a new pandemic? a novel pathogen emerges. Your model is a beautiful piece of machinery, but it's completely empty. You have zero data.
That is the absolute nightmare scenario for any modeler. You have this complex engine and no fuel to put in it. You're flying completely blind.
This is where the paper on challenges in estimation brings up a fascinating idea: structured expert judgment, or SEJ. Now, my first reaction to this was that it's just a very fancy scientific-sounding way of saying we guessed.
It's more like educated guessing under strict quantifiable rules. But yes, at its heart, it's a set of rigorous methods for turning expert opinion into numbers that you can actually plug into a mathematical model.
Because you can't just ask an expert, how bad is this going to be?
Right. You'll get a qualitative answer. I have a bad feeling about this one. Or, it seems contained for now. That's useless for an equation. You can't multiply a bad feeling by the susceptible population.
So how do you turn that feeling into a number? The paper talks about the Cook method?
The Cook method is brilliant and a little brutal. The core idea is that you don't treat all experts as equal. You calibrate them first.
You test them.
You test them. You give all the experts a set of seed questions. These are questions where the true answer is known to the facilitators, but not to the experts. Things like, what was the case fatality rate of the 1957 influenza pandemic? Or, how many people live in Lagos, Nigeria?
So you're checking their homework before you trust them with the real problem.
You're checking two things: their accuracy and their calibration. Are they consistently right? And just as importantly, do they know what they don't know? An expert who says, I'm 90% confident the answer is between 100 and 200 and is right, is more valuable than an expert who says, I'm 100% certain the answer is 150 and is wrong.
It filters out overconfidence. It filters out arrogance.
It does.
Yeah.
And based on their performance on these seed questions, each expert is given a weight. The opinions of the more accurate, better calibrated experts are given more influence when their judgments about the new, unknown pathogen are combined.
It's a way of creating a data point out of pure reason and experience.
It's a way of moving from gut feeling to quantifiable weighted probability distribution that can actually be fed into the model to produce the first crucial projections before the real case data starts coming in.
So we start with human wisdom, but then as the pandemic unfolds, we can switch to harder data, like mobility data.
Yes, this is another frontier. Using real-time data on how people are moving around to fuel the models. The sources mention two main types of models for this: gravity and radiation models.
Gravity models sound like something out of physics.
They're directly inspired by Newton's law of gravitation. The idea is that the number of people traveling between two cities is proportional to their populations, their mass, and inversely proportional to the distance between them. Big cities pull in more people, just like big planets have stronger gravity.
It's an approximation of human movement.
A pretty good one for a long time. The newer idea is the radiation model. It's a bit more nuanced. It suggests that a person in city A will travel to city B to find an opportunity, like a job, only if there are no closer intervening opportunities between A and B.
It's a model of choice, not just of attraction.
Exactly. And the frontier is integrating this real-time mobility data, perhaps from anonymized cell phone data, with these physics-style laws to create a dynamic map of where the virus is likely to travel next. It's no longer a static network. It becomes a living, breathing model of human flow.
So we've covered the foundations, the debates, the frontiers. This is the machinery. But the machine doesn't operate in a lab. It operates in the real world. Which brings us to the final and maybe most important part, the implications.
This is where the elegant math crashes headfirst into the messy reality of politics, ethics, and economics.
And nothing captured this for me more than the Thorin and Gurley paper. They use this incredible metaphor. They describe uncertainty as a monster.
A monster that lives at the science policy interface is such a powerful way to frame the problem.
Because it captures this fundamental conflict of needs. The politician who has to make a decision and sell it to the public needs certainty. They go to the scientist and ask, is this going to kill 100,000 people? Yes or no?
They need a headline, a clear, unambiguous mandate for action.
But the scientist can't give them that. The scientist, if they're being honest, has to reply, well, our model shows a 95% confidence interval that ranges from 10,000 to 250,000 deaths, assuming our parameter for R0 is correct, which itself has a range of uncertainty.
And you can just see the politicians' eyes glazing over in frustration.
They hate that answer. You can't build a national policy on a confidence interval. So this creates an immense pressure for what the paper calls the domestication of uncertainty.
Taming the monster.
Exactly. The scientists are pressured, either externally or internally, to take that messy, probabilistic monster and tame it, to shave off the error bars, to pick a single number from the range, to present one possible scenario as the prediction.
To make it palatable for policy.
But in doing that, in taming the monster, you're also stripping away the nuance and honesty that makes the model valid in the first place.
And that's how you destroy public trust. Because if you present the worst-case scenario as a certainty to scare people into action, and then that worst-case scenario doesn't happen, precisely because people took action, they don't see it as a success. They see it as the model was wrong.
The experts lied to us.
Exactly. And the next time you need them to trust the model, that trust is gone.
This feeds directly into the ethics of it all. The Bartle source on digital crisis technologies has this killer quote, "New knowledge creates new ignorance."
That one really stuck with me too.
What does that mean? How can more knowledge create ignorance?
As our models get more and more sophisticated, as we incorporate real-time mobility data, digital contact tracing, AI predictions, we gain this incredible granular knowledge about the virus's spread. We can see the red dots with terrifying clarity.
But in focusing so intently on those red dots, we become ignorant of everything else.
Yes. The model might tell you that the optimal strategy to minimize infections is a hard, algorithmically enforced lockdown in a specific neighborhood. The model knows about transmission rates, but the model is ignorant of poverty. It doesn't know who in that neighborhood relies on a daily wage to feed their family. It's ignorant of the rise in domestic abuse that happens during lockdowns. It's ignorant of the mental health crisis it might be creating.
So we risk replacing messy, human, democratic decision-making with what the paper calls algorithmic governance.
The computer says no.
Right. We're doing things simply because the model, which is optimized for one single variable minimizing infections, says we should. Bartle argues that modelers need ethical literacy. They have to be trained to think about the consequences of their algorithms, not just for the virus, but for society.
They need to ask not just, is the math right, but is the model just?
And the consequences are often brutally economic. The numbers cited in the Longini and Shaw papers are just staggering.
They really are. The 2003 SARS outbreak, which was tiny by recent standards, cost China over $8 billion. Old estimates for a potential flu pandemic were in the hundreds of billions. The real costs are in the trillions.
So this creates this horrific trade-off, and the Shaw paper talks about using math, something called optimal control theory, to try and navigate it.
It is cold, hard calculus. The model is set up as an optimization problem. You have two things you want to minimize. You want to minimize the number tank the number of infections, but you also want to minimize the duration and intensity of the controls, the lockdowns, the economic damage.
So the model is literally trying to find the mathematical sweet spot between saving lives and saving livelihoods.
In the coldest possible terms, yes. It's trying to find the least bad path between the two catastrophic outcomes of a collapsed healthcare system on one side and a collapsed economy on the other. It's a brutal calculation, but as the paper argues, not making the calculation explicitly doesn't mean the trade-off doesn't exist. You're just making it blindly.
But even in these incredibly complex optimization models, there's one variable that consistently messes everything up. The final, unpredictable piece of the puzzle.
The human factor.
Behavioral fatigue.
The great parameter drift.
The sources mention that most models, especially at the beginning, have to assume that people follow the rules. If the model says 80% mask compliance, it assumes 80% of people wear masks correctly all the time.
But we don't. In the first month of a crisis, when fear is high, adherence is also high, people are diligent, they follow the rules. But by month 6, month 12...
people get tired, they get lonely, they miss their families, they start bending the rules, the parameter drifts. The real-world mask compliance is no longer 80%, maybe it's 50%.
And if your model is still running on the old assumption of 80%, its predictions will be completely wrong. It will underestimate the spread because it has failed to account for human psychology.
It has failed to account for the fact that we aren't just nodes in a network or numbers in a bucket. We're tired, emotional, social creatures.
And any model that forgets that is ultimately destined to fail. The frontier of modeling now is trying to build that drift, that fatigue, directly into the equations, to model not just the virus, but our reaction to it.
So after this whole journey, where do we land? We started with these incredibly simple buckets, SIR.
We moved from there to these intricate, complex networks and realized that hubs and superspreaders matter, but maybe not in the simple way we first thought.
We saw how the math is now grappling with group dynamics and how that can lead to these explosive, cliff-edge transitions that defy our linear intuition.
And we landed on the hardest part. The fact that no matter how perfect the mathematics, it all has to be filtered through the messy human realities of political uncertainty, ethical dilemmas, economic trade-offs, and the simple fact that people get tired of being told what to do.
So modeling is not a crystal ball. It's not fortune-telling.
Not even close. It is a tool, a powerful, indispensable tool for structured thinking in the middle of a chaotic, terrifying event. It's the best tool we have to bridge the enormous gap between what we know for sure and what we absolutely must do anyway.
And maybe that's the ultimate implication. The model doesn't give you the answer. It forces you to ask the right questions about risk, about values, about what kind of society we're willing to be to survive.
That's it, exactly. It's a mirror as much as it is a map.
Before we wrap up, thank you to all our partners, sponsors, and scholars who made this podcast and the research possible. We're truly grateful for your support. And to our listeners, thank you for being part of this journey with us. If you enjoyed today's episode, be sure to subscribe and follow Stack Studios for more informative content and support us on Patreon. Until next time, stay curious, keep learning, and let the search for wisdom guide you forward. Have a great day.